So this final chapter gets into sequences and series, final topic. So at the top, you're going to see obviously the word sequence, and then what we're looking for is the limits of sequences and numbers. And what this ultimately kind of gets into is the infinite limit. So as x goes to infinity, what does our sequence of numbers approach? So if you look at the top there, a quick little definition. Infinite sequence is a set of numbers whose domain is a set of integers. So whenever we're talking about a sequence, we're talking about integers only, greater than or equal to whatever our initial integer would be. This here, a sub n equals 2n plus 1. That's our nth term. That's going to define how we get the terms in our sequence. And then n sub 0 is the initial term that we would start our sequence with. We're going to revisit the ideas of convergence and divergence like we did a couple of units ago. Convergence means the sequence approaches some limiting value, and if that's the case, we would say that it converges to that limit. Divergence would mean that the sequence does not approach a single finite number, therefore that sequence we would say diverges. We're going to start this off with simple little graphs. So if we were to be together in these, I would have you graph these out, so I would still recommend doing that. So it says graph the following sequences to determine if they converge as n goes to infinity. If it converges, state the limit to which it is converging. So we're going to go ahead, what would we need here? Yeah, just kind of have a first quadrant. We're going to label this 1, 2, 3, 4. And just, basically a simple little XY chart would produce these. Take your 1, plug it in. 1 minus 1 would have given us 0. If you take your 2, plug it in for your n here, we would get 1. Take 3, 3 minus 1 would have given you 2. 4 plugged in would give you 3. And what we can kind of see here is if this pattern continued, our values continue to get larger and larger and larger and larger. So in this instance, this would be something that we would say diverges. We're not approaching a finite limiting value. 2. Same thing, just basically start at 1, and then we only need a first quadrant. Take your 1, plug it in. So 1 divided by 1 would, let me make this a little bigger just so we can see what's happening. Silly thing. So 1 is up here. And if I took a 1, 1 divided by 1 would be a 1. If we want the second term in our sequence, you'd plug in a 2. That would give us 1/2. So 1/2 would be right in the middle of the 0 and the 1 here. Take your 3, you're going to get 1/3. So we'd be right around here. Take your 4, plug it in. 1/4 is 0.25. So it's a little bit lower than that. If we do 5.2, and what we should see, even if we plug in 100 up here, 1 divided by 100 is a 0.1. So we're really, really close to the x-axis, but we still wouldn't hit that. What we would see if we continue to go 1,000, 10,000, 100,000, so on and so forth, is that we should start getting closer and closer to the x-axis, which means our limit is 0. So we never hit 0. So that's why we would want to say that this converges to 0, but that would ultimately be our limit. That's what we're getting closer and closer and closer to. All right, so we're converging to 0 in that one. Third one, create a little space over here. So in our third one, same process. Still just need a first quadrant. So again, 1, 2, 3, 4, 5. This one we'll go ahead and plug in so we can kind of see what happens. If I plug in a 1, you'd get 1 minus 1, so that's going to be a 0 over a 1, so that is 0. If we take our 2 and plug it in, we'd get 2 minus a 1 over 2, so we would get 1/2, so let's make this a 1. So 2 would be right about here. If we took 3, plug that in, we'd do 3 minus 1 over 3. that would be 2/3, so 0.6 repeating, so it should be a little bit bigger than this half. If we throw in a 4, 4 minus 1 over 4 would be 3/4, so 0.75, a little bit bigger than that previous one. And if we do one more, let's say we do 5, 5 minus 1 over 5 would be 4/5, so again, a little bit bigger than 0.75 that was before it. Actually, let's make one real obvious. Let's do a 100 here, just so we can see for sure what's happening. If I did 100 minus 1 over 100, I would get 99 over 100, which is really close to 1. So what you would find is, as we go to infinity, so 1, 2, 3, 4, 5, 100, 1000, so on and so forth, what should be happening is here we should be converging to 1. So that's what we would write. This does have a limit that we are converging to. So we would say that this sequence converges to 1. All right, next page, or next problem. This you will want positive values and negative values. So let's start this at 1. Let's start this down here at a -1, and then same process. So let's do 1, 2, 3, 4, 5. Throw that in, throw these values in. So for this one, if I took a -1 and I plug it into this exponent, I would have gotten a -1 squared. And then 1 over a 1 would have been a 1. So I get a positive 1. So we plot that point. If we go to the next term, which is our second term, so take a 2. Now I would get a -1 cubed over 1 over 2. So that's going to give us a -1/2. So actually, let me do this in red so we can see this, because it's going to start to get close to our number. So the second term would be a -1/2. Let me do this in red here. If we go to our third term, the -1, and I do 3 plus 1, this is now a -1 to the 4th power. And then 1 over 3. So the -1 to an even power is going to be positive, and then it's going to be 0.3. So it should be right about here for our third term. And what you'll start to recognize, hopefully, because you're going to see it here, you're going to see it here, you're going to see it in number 7. When we start having this -1 to an n plus a 1, -1 to an n plus a 1, or -1 to just the nth power, what's going to happen is that's going to make us alternate between positive values and negative values. So we're going to go positive, negative as this exponent changes from an odd power to an even power. That's a common thing that we will see throughout this chapter. So something you just want to pick up pretty quickly. Not terribly difficult, but recognize that little pattern. For the next one, for our fourth term, now you're going to get a -1 to the 5th power. So that's going to be odd, which means we're going to get a negative number, and then you would get 1 over 4. So now we're a -0.25. So the third term, or fourth term, should be right about here. If we do the next term, so now plug in 5. So 5 plus 1 is going to get us an even power of 6. So we're going to be a positive value, and then we should get 1/5. So we're a positive 1/5, should be right about here. So what we should see happening is, as we go further and further to the right, even though we're bouncing back and forth between a positive, negative, positive, negative, positive, and then negative value, what we should see happening is we are converging, and what we are converging upon is this x-axis, and then obviously the x-axis has a value of 0, so we would say that this one converges to 0. Okay. Now, number 5, somewhat similar in the sense that this is going to alternate. So let's do this, create a little space here. So because we have this here, the -1 to the n plus a 1, we're going to be bouncing back and forth between positive and negative numbers. So make sure we can have a positive and negative values, so above and below your x-axis. Let's do a 1 up here again, and then -1 down here. And again, first term, second term, third term, fourth term, fifth term in our sequence. Let's plug this in. So if I do a +1 and I plug it in, it's going to give me a -1 squared, so it's going to be positive. And then I would have gotten 1 minus 1 over 1, which is 0. So my first term in this sequence would have been a 0. If we go ahead and find our second term, if we take a -2, plug it into this exponent, you're going to get a -1 cubed. So we're going to get a negative value. And then you would have gotten 2 minus 1 over 2, which is a half. So the second term in our sequence would have been a -1/2. Third term in our sequence, if we take our 3, that's going to give us an even power, so it's going to be positive, and then we would get 2 over 3. So positive 2/3 right around here. Fourth term makes this exponent an odd exponent, so we're going to be negative, and then we would get 4 minus 1 over 4, which is 3/4, but it's going to be negative, so -0.75 would be down here. And then if we do 5, -1 to the 5 plus 1 is a positive number, and then you would get 5 minus 1 over 5, so 4/5, so 0.8. So we're going to be a positive 0.8. So what you should hopefully see as we continue to move further and further right, so as we go 1, 2, 3, 4, 5, and then if we go 6, 7, 8, so on and so forth, what you're going to find is we are somewhat converging in the sense that up here we're converging to 1, down here we're converging to a -1, and as we go further and further and further right, that's what's going to continue to happen. But the fact that we're going to be bouncing back and forth between a +1 and a -1, what that really then means is that we don't converge at all. So because of that, we would say that this one diverges because it's bouncing back and forth between two different values. All right. 6, pretty quick one. So 1, -1, actually, let me create a little space here. What we would have here, we're alternating, and then our constant term is just going to be the 1, that's our nth term, and then we're just going to be alternating signs because we have that little -1 to the nth power. So this one's pretty quick. If we have a +1, you're just going to get a -1 to the first power, so that's going to be negative. If we have our second term, you're going to get a -1 squared, which is a +1. The third one, -1 cubed, is a -1, and what you're going to see is we are again going to be bouncing back and forth between +1 values and -1 values, and when that happens, we're not converging upon anything, which would then tell us that we're actually diverging. All right, then the last one, before we hopefully can shorten this up a little bit, I don't want to get rid of all of that, is number 7. So same thing, we can see that we have a negative raised to an nth power, so we're going to want positive and negative values. I may have to make you squeeze this one in here. So just have this be a half, have this be a -1/2, and then have some x values. We can figure out what our terms are. So our first term, a -1/2 to the first power is a -1/2. So we're down here. But if we do a -1/2 to the second power, so our second term, we're going to get a +1/2. I'm sorry, 1/4. Sorry. So let me erase this. Come on. All right, fumbling around a little bit here. This should be a +1/4. If we go to our third term, -1/2 to the third power should make it negative, and then now we're 1/8, so we're very tiny. If we do the fourth term here, so this is now get a little jumbled. Let me just rewrite this thing. Oh my gosh. As the fourth power, so the even power makes it a positive number, and then 1/2 to the fourth power is 1/16, so really, really tiny. So what we can see is we are bouncing back and forth, positive, negative, but we are converging to the same value in this case, just like in number 4 where we converge to 0. Same thing is happening in this one. So this would converge to 0. Okay? So ultimately, if we kind of look at this sentence here at the bottom, for these numbers 1 through 7, think of our rules as n goes to infinity. Could these rules have been used to determine our convergence? So think back to those rules. If you look at number 1, this had a denominator of 1. So as n goes to infinity, so if we just turn this into a limit problem and just say, all right, well, what's my limit as n would have gone to infinity? What we would have seen or talked about, so I'll make this an infinity here, is the degree on top is a 1. The degree on the bottom is 0, so we have an n to the first. We don't have any here. So this number is just going to get bigger and bigger and bigger. We're going to infinity. So that's why we would say that this diverges. If we look at this one, 1 divided by n, our bigger degree now is on the bottom. So if I did 1 over n, as we turn this into a limit, as n goes to infinity, this would have given us a limit of 0, which is just so happens to be what we converge to. Same with 3. Turn this into a limit. As n goes to infinity, the degrees of these are the same. We look at their coefficients, 1 over 1. That's what we're converging to. Those are pretty self-explanatory. What we need to understand in number 4, because we do ultimately want to, if you look at the rest of the problems on this page, be able to do these a lot quicker than what we were doing, not have to graph them all the time. So as n goes to infinity, so if we set up a limit as n goes to infinity, this little part of the expression, -1 to the nth power or an n plus 1 power, is going to tell us that we bounce back and forth between positive, negative, positive, negative, positive, negative, so on and so forth, forever and ever and ever. The only way this could converge is if this thing here, the general term, the non-alternating part of this, converges to 0. So, and it does. So as n goes to infinity, this term here does go to 0. And if we're alternating and the general term goes to 0, we would see that's going to converge for us. However, when we go to this next problem, create this so we can see it a little bit better. We have the alternating part. So this is going to bounce us back and forth between positive, negative, positive, negative. Notice how this one diverged. The reason that one diverges is because if we just took this part of it, the non-alternating part of it, and ask what is the limit of this as n goes to infinity, with our degrees being 1 and 1 in the numerator and our denominator, the limit of this would have been a 1. But the fact that we are alternating is why we know that we would have been bouncing back and forth between 1 and -1. And because of that, that's why we're diverging. That's why in number 6, I had you go ahead and put this as a 1. So here's our alternating part. Our non-alternating part was a 1. Well, since our limit of a constant is a constant, this 1 here, the fact that we're going to be alternating just bounces us back and forth between +1, -1, +1, -1. That's why that one's going to diverge. Okay. The last one, I want to have you rewrite this a little bit. So let me create some space for you to do that, or at least see what I'm doing. Okay, so I'm going to have you rewrite number 7. Rewrite it this way. So here's number 7, our general term a sub n. We're going to kind of pull out this -1 idea, the -1 to the nth power, and then multiply it by the 1/2 to the nth. Produces the exact same thing that we get over here. But it's a little bit easier for us to understand sort of what's happening with this problem. In the sense that a sub n gives us this alternating part. and what we've talked about is the only way an alternating sequence could converge is if the non-alternating part goes to 0, as it did up here in number 4. But if it goes to something else, like in this problem, where it went to a 1, that bounces back and forth between +1 and -1. So the reason this one converged is because if you think about this, we're going to rewrite this one more time. 1 to the n divided by 2 to the n, and then 1 to the n is really just a 1. So we can get rid of that. Think about what we talked about yesterday or in our previous video, whenever you would have watched that. Our faster growing function here, so this is always a 1 on top, but our denominator is going to get to infinity very, very quickly. It gets large very quickly. So this overall does have a limit of 0. So it's alternating, but since the non-alternating part had a limit of 0, that's why this one would have been able to converge, and it would be converging to 0. Okay? So we now want to use all those ideas, put those together, so that we can get through the rest of these problems a lot more quickly without having to graph them all out. Okay? And that should be what's happening here. So for these next problems, as I look at this, I just realized I went from 7 to 6. So that's awesome. But if you now go to this next number 6, we started these out as limits because that's what we're doing. Eventually, if you kind of look at 9, 10, 11, they're not written as limits, but that is ultimately what we're looking for. So this was our sequence of numbers. Okay, so if this was an a sub n, what we're really thinking of is, all right, what's our limit as n goes to infinity? So from yesterday, what we talked about is the natural log does go to infinity, and then down here would be going to infinity. But what we talked about is the natural log function is the slowest, or I shouldn't say the slowest, but it goes to infinity very, very, very slowly. So what a lot of this really is, so hopefully you've watched yesterday's video and understand it, is which of these functions grows the fastest. So between a natural log and an n is the faster growing function. So as n goes to infinity here, if we calculate that limit, what that should tell us then is overall, since our faster growing function is on the bottom, that our limit is 0. So we would say that this would converge to 0. All right. Number 7, as n goes to infinity, what that would give us is x to the 1 over, and then think about this denominator becoming an infinity. Well, what that would give us is x to the, and as n goes to infinity, this should behave more and more and more like a 0. And then anything to the 0 power is a 1. So this would have to converge to 1. 8, I would strongly recommend with these rewriting these real quick. So n squared, an nth root means we have a 1 over an n. And then through simple little algebra here, if I have a power raised to a power, we multiply those. So if we simplify that, what we really have is n raised to the power of 2 over n. So then if we now calculate this as a limit and think, all right, what happens as we go further and further to the right? Our inside is going to become a very, very big number. So 10, 100,000, million, 2 million, 1 billion, so on and so forth. However, what we would have happening in our numerator here is as our n is getting larger and larger and larger and larger and larger, the exponent here should be going to 0. So despite this getting huge on the inside, the fact that your exponent becomes a 0 would still tell us that our limit is a 1. So this would converge to 1. 9, similar. Rewrite this first. So 3 to the n to the 1 over n. And this would be 3 to the 1 over n times n to the 1 over n. And then again, same thing would happen. This is always a 3, but it would become 3 to the 0 power. This would become a huge number, but it wouldn't matter because it's ultimately going to be getting raised to a power of 0. So we would have a 1 times a 1. This is going to converge to 1. 10, just some old rules here. Degrees are the same. N to the first, n to the first. We look at their coefficients. -2 divided by a +2 tells us that this should converge to a -1. 11, as n goes to infinity, degree of 2 on top, a degree of 1 in your denominator. This has a limit of infinity. So this is the first one of these that we've been doing where we would say this diverges. 12. Think about what would now be happening here as n goes to infinity. What this would do is bounce back and forth between, if we were to graph it, 1 and -1. So 1, -1, 1, -1. So what we would have with this is 1, and sometimes we're going to be adding a +1. Every other time we're going to be doing 1 plus a -1. So let me make this a little clearer. So what this should bounce back and forth with, if we actually graph these, and graphing these is not a bad idea. So if we were to do a quiz or whatever, throwing down a quick little graph, seeing what happens is not a bad idea. What would happen is this would always produce either a 2 or a 0. So if we were to graph this out, you're just going to bounce back and forth between 2, 0, 2, 0, 2, 0, 2, 0. Sure. And then what that would give us, that's Isaiah, in case you guys heard what to. Okay, I just paused you, so I'm not completely certain where I was at. Just if we were to graph these 2, 0, 2, 0, 2, 0, bouncing back and forth would tell us then that ultimately this is one that would diverge. Gotta love kids, right? So diverges. All right, 13. What I would recommend with these, a lot of times when we do these, separate these into a product of two separate terms, even though it's written as a fraction. So let's take this -1 to the n plus 1. Let's kind of pull it out and then rewrite the second part as 1 over 2n minus a 1. Okay. So what this would tell us is this is the alternating part. We know we're going to be bouncing back and forth between positive, negative, positive, negative, positive, negative. The only way an alternating sequence could converge is if the non-alternating part, so this guy, if that non-alternating part goes to 0. So as n goes to infinity, this does in fact go to 0. So because we're alternating, but the non-alternating part's going to a 0, we would say then that this thing does converge. And in this case, it converges to 0. All right. 14. Kind of a new little problem here. Haven't seen one like this yet. So as n goes to infinity with this one, so limit as n goes to infinity, think about what is happening in terms of which of these functions grow faster. Does the sine grow faster, or does the function n grow faster? All right, and what you would hopefully kind of think of is as n goes to infinity for the sine curve, all the sine curve does is this. So while it's not a constant, we don't really grow at all. We're going to be bounded between a 1 and a -1 at all times. So the sine of n doesn't really increase to infinity at all. While in your denominator, this is going to become a 10. So if we divided all this, let me do it over here, we would divide that by 10. Oops. And then 100, 1,000, 10,000, 100,000. We keep adding all these zeros, whatever this number ends up being, 100 million. And then all you will ever get in your numerator, so as this just bounces back and forth, the only thing you'll ever get in your numerator is some value between 1 and -1. So what ultimately happen is that's going to be getting smaller and smaller and smaller and smaller. Okay. That's one that I can show you real quick. This is usually one I would have you with your calculators out and graph. So if I were to graph this, so sine of x, and then divide that by x, and then hit graph. And then what we would see, let me make our window a lot bigger. So our x-men will be 0. Let's go out to 15. Graph that. You'll see how that gets tighter and tighter and tighter to the x-axis. Okay, even if I make our window a little bit bigger, let's say 50, you can see it pretty much is just hugging the x-axis that whole time. You can't really tell the difference between them. Okay. All right. 15. Let's rewrite this thing. 2n over n plus a 1 all to the 1/2 power. Okay, so think about what's going to happen with this as n goes to infinity. What would happen on the inside is on the inside, this is going to have a limit of 2, and then it's being raised to the 1/2 power. So we would say that this converges to root 2. All right. 16, pretty straightforward one. As n goes to infinity, the only thing that would impact is this. Our faster growing function is in our denominator. So since the faster function is growing in our denominator, this will behave more and more like a 0. And as that becomes a 0, then we're ultimately just taking the sine of pi over 2, which means we would be converging to 1 because that's what the sine of pi over 2 value is. 17, the natural log. You're going to want to rewrite this. A lot of natural logs, when we start evaluating them and using those, you're going to want the simplified version. So since we're subtracting 2 natural logs, we can divide them. Or write 1 natural log and divide their composites. And then that's our general term. And then now think as n goes to infinity, what's going to happen? Inside of the parentheses, so if we just focus on what's inside the parentheses, this is going to have a limit of 1. And we'd be taking the natural log of 1, which is 0. So this guy would converge to 0. Okay. 18, this is kind of the first one where we don't necessarily know which function grows faster. So if we kind of revisit L'Hopital's rule from the other day, we can take the derivative of these and get 1 over n, and then as these 2's cancel, we get another 1 over n, so that our limit is just going to be a 1. And because that limit is a 1, they're growing at the same rate, but that then is also what they're converging to. So we would converge to 1. All right. Now, these next handful of problems are really, 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 really important. Okay. This is one of the bigger things that you have to get down. This is counterintuitive as well. So this is something that you just want to kind of be aware of. And I'll kind of show this with the calculator as well. Normally you'd have your calculator in class. I'd have you throw in a bunch of these so you can see what happens. But this is something you want to get memorized. It's counterintuitive. It's one of these things in math that doesn't make sense to just look at. It requires a little bit more exploration and playing around a little bit to try to figure out why that doesn't work. But if you look at number 19, what I'm going to have you do is I'm going to have you first graph, how do we want to do this? Graph on the calculator. We're going to graph this as if it is a 1. All right. So we're going to say this is 1 plus 1 over n raised to the nth power. Okay. So let me go to our calculator. And what we're graphing is, what are we graphing? 1, the quantity 1 plus 1 divided by n. So in this case, x. Although we can change that to sequences if we wanted. And then we're going to raise that to the nth power. And we are going to, oops, let me delete that. Graph this. All right, so notice what that looks like. What you would probably have anticipated is, hopefully, for understanding what's going on here, if I would have changed this to this problem, what we would have hopefully kind of been thinking is, and if you thought this is sound, it makes sense, this is why it's counterintuitive to what you would think would happen. You would think that this guy here would have become a 0, and all we really end up with then is a 1 plus a 0 on the inside raised to an increasingly big number in your exponent. But if I had a 1 raised to anything, you would have thought that this would have converged to 1. If we look at our calculator, however, you're going to see here's 1. This thing is not, this thing is not approaching 1 at all. It's approaching up here. It almost looks like it's approaching 3, right? It kind of looks like it's leveling off towards 3. All right, so that's weird. If I have you go to number 20, Let's see here. And we graph this one. So let me change this to be a positive 2. And so all I'm going to do, go back into my calculator. I'm going to change this. Let me move over to a 2. So again, your thought probably, hopefully, if we're understanding what we did earlier, I'm going to split this up. I'm going to do n divided by n plus 2 divided by n, all to the nth power. So I again get a 1 plus 2 over n to the nth power. So these, let me clear this up a little bit. These two problems, when I have this be a 1, these should look very, very, very similar to each other. They each have the 1. They each have our plus, and then the 1 over n, 2 over n, and then all to the nth power. So if we just kind of think what should happen, this should go to 0. We should end up with 1 plus a 0 to our growing number in the numerator. This should have a limit of 1 again, just like that previous one. All right, but then obviously we know that didn't happen. So if we now go to this next one, we hit graph. You'll see we can't even see what this is doing. So let me increase my window. This 10. What did I do here? Sorry. That needs to be 0. And we want y max to be 10. Let's try this again now. But you can see it does definitely level off towards something. All right. So what this is leveling off towards, believe it or not, let me go to the second one just to prove this, is, oops. All right, so see that, e squared? Let's go ahead and graph that. See how that expression is leveling off towards e squared? Let's revisit the one, and then notice kind of what that meant. See how the numerator here was a 2, and the exponent here was a 2, and the e? If we go to what we had before, let's change this to 1. Let's change this to 1. We'll graph it. So notice what this levels off towards. Notice how this is leveling off towards y equals e. So we said it's about 3, but think about what e was. It was 2.7. So this expression is leveling off towards e. And it's, again, power of 1 in the numerator of that fraction, power of 1 in the exponent for our e. So what that is telling us, we go back to our problems, is what these really converge to, and you'll just want to get this memorized. And we've actually talked about this. Is whenever you see this expression, let me erase this also, what this expression converges to is e, and then to whatever the numerator is in this fraction, and in this case it's e to the x. So for this one, when we simplify this, 1 minus 2 over n to the nth power, that should converge to e, and then notice how your exponent is this negative 2, e to a negative 2. If you go to 21, if we simplify this, this should be 1 plus 3 over n to the nth power. What this is going to converge to is e cubed. It stems off the idea that what the number e is defined as, and this is what we've talked about a little bit, you probably did this a little bit last year, is this expression 1 plus 1 over n to the n, the continuous compounding interest formula. That's where e comes from. This is e to the first power. That's what this levels off towards as n goes to infinity. So you want to definitely get those memorized. It's a pretty important thing. It's something you're going to see a lot, and it's something that is counterintuitive, which is why you just really want to kind of commit it to memory. Okay? All right, other than that, pretty straightforward. 22, 23, we can do these quickly. We've already done enough of them. The exponent here is going to turn into a 0. Anything to the 0 power is a 1. So that converges to 1. This one we've already done. It was an earlier problem, I think, if I remember correctly. Yeah, it's number 8. So if you look at number 8. All right, we've already done that, so we're skipping it. All right, then finally, let's revisit what a factorial is, because we have these guys now hanging out. So this is a new little thing that I think you've talked about before, but we have talked about it. Have not talked about it, but you'll see factorials in 24. You're going to see a factorial in number 25. You're going to see some factorials throughout this chapter, so something that we want to get comfortable with. So again, first, I'm going to separate this. This is a negative to the nth power, so this really could get rewritten as a negative 1 to the nth, and then a 4 to the nth, and then we would divide this by the n factorial. So when we did the rates at which functions grew yesterday in the previous video, we had kind of a hierarchy. Natural logs of n's, logarithms grow the slowest, and then if we have n to the first, n cubed, the bigger the degree is, the faster we grow. Then eventually we got e to the n, 4 to the n, exponential functions, whichever one has the biggest base grows faster. If I can squeeze a 10 to the n here, those grow the fastest. Well, we kind of have a new guy in town here, and that's 4 to the n and n factorial. And I'll show you again on the calculator. Sorry, it's making this video rather long, but a pretty important idea because we deal with factorials a lot now. So I'm going to graph in this one 4 to the nth power. And then down here, I'm going to graph n factorial. So n is going to be our x. I got to remember where this is at myself. Stat. Give me a minute as I fumble around here. Okay, I found it here. I had to pause you guys so I can remember where it was. But if you go to your math key, go underneath probability, go down to number 4, you'll see your factorial symbol. Hit that, x factorial. So when we graph these, I'm not even going to graph it. We're just going to go directly to our table. So if I go second table, pull this down so you can see this. Hopefully you can see this. If we look at this, you're going to see that initially I had the exponential function first. So the blue is the exponential function. The red is our factorial. So the blue one is initially in the lead. All right, you can see here it's off to a huge lead. But as we continue to scroll on down here, it doesn't take too long for our friend the factorial. There we go. So you're going to see at the 7th term, the blue is still bigger than the red. At the 8th term, our blue, which is the exponential function, is greater than our factorial. But then by the time we get to the x value of 9, exponential function is still incredibly fast, but it still is nowhere close. The factorial is already 10,000 bigger than what our exponential function is. It doesn't seem like factorials would grow that fast if you really think about it, at least to me. Again, it's something that's sort of counterintuitive. But if you just did 9 factorial, which doesn't seem like a huge number, it really is. It's already 362,880. So factorials grow faster than exponential functions, and we can see that there in our table. So since our faster growing function is in our denominator, this does in fact have a limit of 0. So this we would say converges to 0. 25. The factorial then, since we know the factorial is now the king, they grow faster than an exponential function. We now have exponential functions teaming up against him. So now they join forces to try to knock off the factorial. We don't have to graph it. You're at home. You can graph it if you like. But I promise you, the factorial still is victorious. It is still faster than both of those exponential functions together. So since our faster growing function is now in the numerator, this has a limit of infinity. So this would tell us that we diverge. Okay? And then last but not least, see, I'm going to squeeze this in less than our 48-minute class period, is this guy. So this now, be careful. This is the combination that we need to get memorized. This is the same combination that we saw in, if I can pull this down a little bit, number 19, number 20, number 21, that you just need to get memorized. what happens as n goes to infinity is this is going to become e to the first inside. And then we would have been taking the natural log of this, which is a 1. So we would say that this converges to 1. Okay? So that's that. Sorry it's so long here, but this is a pretty key principle. It's the basis of pretty much everything we do for the rest of this chapter, so I didn't want to skip over this too much. So enjoy the rest of your day. If you have, again, any questions, please reach out, let me know. All right, I'll see you guys later. Hopefully, have a good day. Bye.